This conference will now be recorded.
Very good morning, students. Today we'll be discussing simple microscope from ray optics chapter. So we have so far discussed about spherical mirror. We have discussed the spherical lenses, refraction through spherical surface, etc. Lens makers formula, thin lens, combination of thin lens, etc. We have discussed already. So today we are going to start discussing about the instruments where we use spherical lenses or spherical mirror. So simple microscope, we have to read, actually we have to learn three instruments, optical instruments: simple microscope, then compound microscope, and third is telescope. And here we have to learn two things. One is terrestrial, okay, terrestrial, and second one is astronomical, nomical telescope. Okay, so optical instruments, these are the things we have to learn. Today we are going to learn only simple microscope, and we'll see what are the problem questions may come, and the important points to be noted, and all those things we'll discuss, and we'll take up few numerical examples so that we can be thorough about the working principle and related theories of this simple microscope. Okay, so what is a simple microscope? Actually it is simply a magnifying glass. Okay, a simple microscope is actually simple microscope or a magnifying glass. Magnifying glass is a short focal length. A convex lens of is a convex lens of short focal length. Okay, so simple microscope or a magnifying glass is a convex lens of short focal length. Okay, short focal length, and it is actually it is held very close to the eye, close to the eye. See, for example, watchmakers. Okay, watchmaker microscope. Watchmakers, they use on microscope. They place it very close to the eye, right? Watchmakers microscope. This is one of the simple microscope. Like example, all of the examples of simple microscope. Okay. Now what we are going to learn here? See, we have to learn, like we have to just find out what is the magnification. Our aim is to learn magnification. Microscope. What is the use of microscope? Microscope we use when a very tiny object we want to see, but in a enlarged form, right? Very small things we want to see, very small thing, but we want to see it at, like we want to see it enlarged, okay, or bigger size, okay. So for that, generally microscope is being used. Okay, so we have to see what is the magnification. So, or the working principle, let us first learn what is the working principle. There are two situations or two ways to use this simple microscope. So one situation is that when the image is formed at the least distance of distinct vision. Least distance of distinct vision. Okay, let me just do one thing. Let me keep this figure here as well. Okay, so that we can refer to the figure. So there are two situations when we have to explain the working principle, or we have to find out the magnification at two situations. Okay, one is when image formed, image is formed at least distance of distinct vision, that is D, that is denoted by D, least distance of distinct vision. And the second thing is when the image is formed at infinity. When the image is formed at infinity. Infinity. Okay, these 2 points we have to learn. Like we have to find out the magnification when the image is formed at least distance of distinct vision, that is denoted by D and caps D, as you see, and when the image is formed at infinity. Okay, let us just derive the formula for magnification at this situation and at this situation, and then let us try to solve some numerical problem. So before we go to this derivation, let me tell you what is least distance of distinct vision. Least distance of distinct vision. See, it is the minimum distance from the eye. It is the minimum distance from the eye at which the eye can see, the objects, clearly and distinctly. And distinctly. Without any strain in the eye. Okay, without any strain strain in the eye. Is called the least distance of distinct vision. And it is denoted by capital D. Okay, capital D. It is denoted by capital D. And for a normal eye, this D is actually 25 centimeter. Okay, this is actually called least distance of distinct vision. Okay. Now there is one more term. Let us first learn that term itself. Near point for a eye. What is the near point? Similar to that, the nearest point from the eye at which an object can be clearly seen. An object can be clearly seen. Clearly seen by the eye. Okay, it is also the nearest point from the eye at which the object can be clearly seen by the eye. Okay. So this point near point. Okay, this is called near point, and it is actually representing the same thing, D, and that is 25 centimeter for normal eyes. Okay. So this is about near point and least distance of distant distance we have already discussed. Now let us find out, or let us try to understand the working principle. So for that we have to just erase this part. I'm just clearing this part. So look, I'll just take a situation when the final image is formed at first situation, when the final image formed at least distance of distant vision. Okay, so this is the first agenda. Let us try to understand this. See, ray optics means you need to take the help of ray diagram and geometry as well. So look here, when an object AB, see this is the object. See, you know, you have to see the enlarged image, right, for a convex lens. So how do you get an enlarged image? When you keep an object between the focal length and the optical center, right? That is the normal situation, right? So for that case only, there will be the image which is a virtual image and enlarged image. Okay, as you see here, see this is the lens, convex lens, and this is the object AB, which is placed vertically on the optical axis, sorry, principal axis. Okay, and see, if we just go with the principle of image formation by lens, see parallel ray, after refraction it will go through the focus, kind of that, and then ray which is actually obliquely going, or so, which is going through the optical center, it actually passes through. So if these two refracted ray meet somewhere, then we get real image. But here we can see that they are having no chance to meet each other, so we'll not get any real image at this particular situation. So if we retrace back, then we get this a prime point. Okay, a prime point. Okay, so then we get this image a prime, b prime. So when an object AB is placed between the focus and the optical center, a convex lens, a virtual erect. See, virtual erect. Erect means both are actually having the head upward and leg downward. So both of them should be like that. Okay, object and image. So then image is called erect image. Okay, if there is no vertical inversion. Erect image, virtual image, and also magnified image. See, magnified means, see, the object was AB, this much small. Now the object has become A prime, B prime. Okay, so sorry, image has become A prime, B prime, which is, see here, let me write it here. Object is AB and image is A prime, B prime. Object is AB and image is A prime, B prime. A prime, B prime. Okay, so here see, A prime, B prime image is much larger than, like, if you see in terms of height, A prime, B prime, so this image is A prime, B prime. You can see this A prime, B prime is much greater than AB. This is actually enlarged image. We can see virtual image, and also there is no vertical inversion. So look here, the microscope is so adjusted that the image A prime, B prime is at D. Image is formed like this, but then The lens is so adjusted that the image is formed at image is formed at this O prime, OB prime, this distance OB prime, this distance has to be D. Okay, D means least distance of distinct vision. Okay, so this is actually the object distance, you can say. So it will be actually object distance when we say this will be minus D, sorry. Now D distance is actually very close to the eye, position of eye. As you see in the figure, this eye is very close to the lens. So whatever this lens is doing in terms of lens from this lens or eye, or angle measured from eye or lens, the same, because the eye is very close to the lens itself. Okay, so here we have to find out now. See what we have done. I'm just summarizing what we have done here. See, this is a this is a convex lens. It has so we have placed the object AB in between focus. Suppose focus is somewhere here, focus and the optical center. So there will be a virtual erect and enlarged image will be formed, A prime B prime. Okay, and the lens is so adjusted that this image position is at exactly distance D. That means U is equal to minus D. Okay, I'm sorry, this B is equal to minus D. U is equal to already something is there, B is equal to minus D. Okay, so at this situation, see, we have to find out the magnifying power. So we have to find out the magnifying power. Magnifying power of simple microscope. So magnifying power of simple microscope, we will find out. See, the magnifying power of a simple microscope is defined as the of the angle, ratio of the angle that the image formed at the optical center or at the eye. And another, okay, to the angle subtended by eye to the object. Okay, let me first write it so that you can understand it clearly. So magnifying power of a simple microscope, let me write it here like this: magnifying power. So angle subtended by the image. Angle subtended by at least distance of distance. Least distance of distance vision. Okay, so I'm writing just this D, and in the down angle subtended by the object at least distance of distance vision. There here also. Is an angle subtended by the images so angle subtended by the image at the least distance of distance of distance vision. Okay, now see, since the eye is very close to the lens, the angle subtended at the lens must be equal to the angle subtended by the eye also. Okay, so we have, see, D is already seen here. See, we have to find out the angle subtended by least distance of distance vision means what? See, this image is actually subtended by image. So this A prime, B prime is the image, and if you look through, you will see this. So the angle beta is that particular angle which is actually subtended by the image, in fact this angle. So this is beta, and the angle subtended by the object at the eye when the object is placed at the least distance of distance vision. You can see here. So beta we have got. See this magnifying power. If I write m, then angle subtended by the image by the image at least distance of distance vision will be this f. I'm sorry, this is beta. This is alpha. This is called alpha. Look this, the object subtended by an angle so this is beta by alpha. Now see, m is equal to beta, so this can be written actually like this. Beta means what? Beta means, okay, so let me just write it tan beta, and this could be written as tan alpha. Tan beta is what? So this particular, so perpendicular by base, AB by OB. Okay, let me just go to this page. Here we haven't done anything. So we have got m is equal to beta, that is the angle subtended by the image at the length when the image is formed at least distance of distant distance, and this beta by alpha. Alpha is the angle subtended by the object at the optical center. So alpha is here. Okay, now we have got see tan beta by tan alpha. This I can write, and from this figure how we can write as tan beta. So tan beta means what? Tan beta means this particular part. We'll just go with the ratio of the arms itself. So they say this will be actually AB by OB, AB by OB divided by A prime B prime O prime B, sorry, O prime B, as you see here, this one, okay, alpha. Actually, see, we have to find out the angle alpha. Alpha is the angle subtended by the object at the least distance of distant distance. So that's why here, okay, alpha is taken here, not here. Otherwise, alpha beta will be the same. Okay, so this is the one. So A prime B, that is the, okay, A prime B is the same thing. Tan alpha means perpendicular by base. So perpendicular is A double prime B prime. A prime B, sorry. This is OB prime. So look, this A prime, A double prime B prime, this is nothing but B prime. So this, oh, I'm sorry, this is equal to AB. So AB will be crossed this one and this one. So it will be OB prime divided by OB. Okay, OB prime divided by OB. So what is OB prime? OB prime is here, minus D. So M is equal to minus D. And this OB, look, this distance, let us take this distance as X. Okay. Okay. So now look this. we get d by x. So this is actually magnification, but we have to express it. Express this in terms of UV and F. Okay, this magnification in terms of UV and F. Okay, so look, we know 1 by V minus 1 by U is equal to 1 by F. Okay, 1 by F. Now, if we put that, so V is actually this is X is equal to 1 by F. So we have to find out actually d by x. Let us just multiply it with d. So 1 by f is equal to minus d. Okay, just let me get you some space. Let us just clean this portion itself. So we have got this dx, so d by x is equal to this. We have to actually write in terms of u, v and f. So that is what we are going to do. See, 1 by v minus 1 by u is equal to 1 by f. So here we'll put 1 by minus d, then u minus 1 by u, 1 by f. So u is actually at x distance, right? And that is with minus sign, obviously. So this goes, okay, let me just complete it. Multiply d on both sides. Okay, so d by x is actually 1 plus sorry, this 1 plus d by f whole into m. So this will be actually magnification for the image formed at least distance of distribution. So we can see from this figure that when this is x actually, okay, when f is larger, focal length is larger, then what we see? Magnification smaller, m is smaller. Okay, so that means for short wavelength, when f is small, is short or small value, then when f is shorter, then focal length will be larger. Focal length will be greater or larger, greater. Okay, so this is for image formed at D. Okay, so here D is 25 centimeter for a normal eye. If we have to find out for focal, this is the focal length of the microscope or the lens used. Okay, so this is one case. Another case, let us just try to understand when the image is formed at infinity. When the image is formed at infinity. See, to have image at infinity by the convex lens, what is the criteria? Criteria is that the object is placed at in principal focus. So when the image is seen near point, then it is actually straining to the eyes. So that's why it is easier to, but it is easier to see things at very large distance. Then our eye will not be getting strained. Okay. So for that, actually, very often we want to see the object at large distance so that we can see it properly without strain of eye. Okay. Now see, if we keep the object at any of the focus, like at focus, then what will happen? The image will be formed at infinity, right? You can see this optical ray, sorry, optical center, through optical center, it is just going like this, and after say refracting like this, parallel ray we have taken, and then this is converged. Okay, so image will be formed at this, at infinity. Now look, this is at focal length, this is the beta, the angle. So the magnification is actually this, the same definition. Magnification is the angle subtended by the image at infinity. Okay, at the eye to the angle of magnification by the object at eye when situated at the least distance of distant vision. So actually what we have to do, we have to take these angles. Okay, it is defined as the ratio of the angle formed at formed by image at the eyes of angle like at the eye. Actually, this angle, this is the angle. See, this is actually created by image. This is also another image. Sorry, angle, same angle actually. So see, m is equal to beta by alpha. Alpha we know, right? So what is alpha? Alpha is this. Suppose your eye is here. Okay, eye is here. Okay, eye is here. Then this is alpha. This is actually object. This is a b. H is the height. This is actually d. So always this alpha is taken as the angle subtended by the object. Okay, when we see or focus our eyes for the least distance of distant vision. So this we have to put here now. Okay, so see, m is actually tan beta by tan alpha. Tan alpha. So tan beta could be written as h by f. You look this here. Tan beta is h by f, and tan alpha is, so this is d, this is h. So h by d. Okay, h by d. So it is actually d by f. D by f. See, here one thing you have to always remember is that how do we define the magnification? Magnification is always defined. Beta is actually angle subtended by image at the eye or at the lens or at the optical center. Angle subtended by the image, subtended by the image. And alpha is actually the angle subtended by the object. Okay, object at, when object is placed at the distance of distinct vision. Okay, so that is the situation. When the object is placed at the distance of distinct vision, then the angle subtended by that object is actually called near point, and that is for normalized d. So this is how we have to find out. So what we have got for two settings. For one setting is first setting. So m is 1 plus d by f when the image is formed at least distance of distinct vision. Okay, this particular formula. So in the second case, m is equal to d by f when the object is placed at the least distance of distinct vision. Okay, and the image is formed at infinity in general. Okay, because the, okay, so this is the magnification in the second case when the image is formed at infinity. When the image is formed at infinity. Okay, so magnification, this is the magnification when the image is formed at infinity. Okay, infinity. So look these two magnifications, and this is the magnification when the image is formed at least distance of distant vision. For a microscope, these are two magnifications which we need to remember. And look here, so this among these two, so when the image is formed at infinity, the magnification is actually less by 1. Okay, but you know the magnification may be less than this when it is formed at near point, but the thing is that the image is actually comfortably seen without any or without much stress for the eyes. Okay, we'll now see some uses of this microscope. See, as I said, watchmakers, jeweler makers, like jewelry makers or jewelers, watchmakers, jewelers use this microscope, right? Second thing is magnifying. In magnifying printed letters in a book, texture of fibers or thread or a cloth, engraving, details of stamp, etc. Magnifying glass is used in scientific laboratories also. Okay, science laboratories. Okay, labo sorry laboro laboratory, science laboratory. Okay, I'll just summarize what we have done. We have done today simple microscope, which is just a convex lens of short focal length, and we had to find out magnification for two situations or two settings when the microscope is so adjusted that the image is formed at least distance of distance vision, that is d. So in that case, the magnification is 1 plus d by f. Okay, 1 plus d by f. And the second case, second is when the image is formed at infinity. Okay, so in that case it will be d by f. Okay, so these are 2 points we need to remember. I'll just stop it here for today. The numerical problems will be taken in the next class, maybe tomorrow, and then we'll go ahead with compound microscope. Okay, so thank you for your patience. Bye for today.